Hi there, another review? For a change, this is the BM550 battery tester kindly sent in by Kingbolen. I'm not paid for the video, but since I'm allowed to keep the tester, I mark this video as a promotion. From my previous reviews, you know that this doesn't stop me from sharing all my findings with you. This sheet is all the instructions you get, and it doesn't look all that complicated, but let me tell you, I've spent way more time on this than on any other review recently, and I learned a great deal about battery testing. It's a neat looking unit, and it comes with impressive alligator clips and test cables. These test cables are surprisingly soft for their diameter. That's a bit strange and something to look into. The tester itself has no battery compartment because it's powered from the battery under test. For our first test, I decided to use my biggest power supply as a stand-in for a 12-volt battery. When I connect it, the tester springs to life and wants to know the nominal battery voltage. You can choose between 6, 12 and 24 volts. Default is always 12. At this stage, it doesn't check what the actual voltage is. Pressing OK and we get to choose a CCA value. More about that in a moment. I choose the lowest possible value, which is 100. And off it goes, doing its tests. The result for this power supply is a CCA of 76, which is apparently normal. Pressing the down arrow brings the next item, which is the state of health, or SOH, of 59%, also determined to be normal. The state of charge, or SOC, which is 0%, which is strangely determined to be normal, but would worry me if that was a real battery. The battery resistance is shown as 33.7 milliohm and rated normal as well. And the battery voltage at 11.87 volts, again normal. And then the menu repeats, showing CCA again. Pressing the red return key goes a level up, in this case back to the CCA selection. To find out what happens during the test, I inserted a resistor between the tester and the power supply and monitored the voltage drop across it. I had to use a 1 ohm value because the 10 milliohm shunt I tried first produced a too small voltage drop, disappearing in the noise. Whatever the tester does, it does not use very high currents. Changing the scope trigger from auto to normal to capture only when something is happening. And there it is. That is all that happens on the wire. The tester itself takes quite a while longer calculating or whatever it does before displaying the result. Because of the extra 1 ohm resistor, the CCA value has dropped from previous 76 to 5, rated poor. Health is now 0% and rated poor. State of charge is still 0%, but now this is apparently also considered poor. The resistance is strange. I inserted a 1 ohm resistor in series. I would have expected the result to be at least 1 ohm plus some change, but this is just barely more than half a ohm. Weird. Finally, the voltage has dropped by 4 millivolt. Another thing to investigate. A closer look at the scope. Ignore the blue trace for now, which is the battery voltage. The yellow trace is half a volt per division vertically, so we are looking at pulses of slightly less than 1 volt. Across 1 ohm means each pulse represents about 1 amp of current. The horizontal scale is 100 milliseconds per division, and the whole test is finished in slightly more than 4 divisions, about 420 milliseconds or so, less than half a second. Changing the horizontal scale to 10 milliseconds per division shows that the signal is about 4 milliseconds high and 4 milliseconds low. That is, we have a period of 8 milliseconds or a frequency of 125 Hz. Instead of counting the pulses, since the whole test lasts about 420 milliseconds and each pulse lasts 8 milliseconds, we can calculate it must consist of about 52 pulses. To be clear, these are not exact values, just ballpark. It doesn't really matter. All I wanted to see what the thing actually does. I decided to repeat the test, setting the CCA value to the highest possible value of 2000. I wanted to see if that changes anything. The reported values on the BM550 display are exactly the same as before. On the scope, the pulses are exactly as before as well. Here's the end of the pulse train. So, what is CCA? It stands for cold cranking amps, and the term may be something that the folks in the US are more familiar with than we here in the UK. I think here it's called starting amps, but most batteries are sold based on capacity measured in amp hours. On the Amazon UK webpage for this tester, there is a helpful table for converting between amp hours and CCA. I found various slightly different definitions of what CCA is. One is the number of amps that a 12-volt battery can deliver for 30 seconds when the temperature is below 0 degrees Fahrenheit, which is minus 17.8 degrees Celsius, while maintaining a voltage of at least 7.2 volts. This seems more to be about the short-term max power delivery under difficult circumstances, while capacity in amp hours is a long-term measurement of how long a battery can deliver a current from fully charged to fully empty. This makes the conversion between CCA and amp hours somewhat questionable in my opinion. I have read various conversion factors on the web, like amp hours times 7.5 is CCA. For what it's worth, here's the table from the Amazon site plotted as the blue trace. It's not exactly a straight line, as a simple multiplication with a constant would produce. In fact, the factor shown as a red trace is varying between nearly 20 for low amp hours and 5 for high values. Technically, I can imagine there is some relationship and correlation. A battery with more amp hours is bigger and has a lower internal resistance and will be able to deliver more amps in any condition, including cold cranking. So yes, more amp hours means more CCA and vice versa. Let's consider what a battery may look inside as a simplified electrical model, not mechanically or chemically, as for example lead acid car batteries are of course very different from a lithium 18650 cell. A simple model would be an ideal voltage source with a 0 ohm internal resistance and, at least short-term, constant VB. The internal resistance of the electrolyte and contacts inside the batteries are lumped together in an imaginary series resistor, RS. For most normal batteries, RS is well below 1 ohm, but button cells usually have a higher RS value. RS rises as the temperature of the electrolyte drops and also when the electrolyte ages, and other effects based on the accumulated charge-discharge cycles. If you measure the battery on its terminal with a decent voltmeter with megohm input resistance, the voltage you measure will be the same as VB, because so little current flows there is practically no voltage drop across RS. This means even a very worn-out battery with high RS still reads a high VB when measured with just a voltmeter. Volts alone is therefore not a good way to determine the health of a battery. The CCA case represents an extremely heavy load, so much that only half of VB is available on the terminals, the rest is dropped in RS. This means of course that the starter motor represents a resistance of about the same value as RS. The maximum current this battery can deliver is limited by RS, which is easy to see if you consider shortening the battery terminals, but it's also true for the less extreme case of CCA. If RS rises as the battery ages, it means less maximum current can flow, more voltage is dropped at the same current, and therefore the battery's CCA value goes down. The value of measuring CCA, or really RS, is that it provides an instant indication of the health of the battery. Of course, an aged battery also has less capacity, but counting amp hours to determine health is very time consuming. First you need to charge the battery fully, then discharge it fully while keeping track of the current and time, and at the end you have an empty battery, so you need to recharge it again before you can continue using it. Back to the battery tester at hand that claims to measure CCA. It turns out that this model is too simple because it doesn't consider transient loads, which is what this tester does with its pulse trains. To model that, we need an additional circuit consisting of another resistor RT and a capacitor CT. If you just consider a constant DC load, this means the series resistance RS for the previous model is now split into two resistors, so the value of RS in the simple model is the same as the sum of RS plus RT in the new one. CT models the behavior of transient load pulses. CT is charged to the value of the voltage drop over RT. If a sudden current spike arrives, the voltage drop over RT would increase, but that is delayed or dampened because CT needs to be charged further before any change can happen. Another way to look at it is that the charge in CT is in series to VB, and therefore on a very short term, shores up the output to satisfy the sudden pulse demand. As far as I understand, RT represents the losses incurred by transferring charge in the electrolyte or polarization. If you have a high transient frequency, there's no time for the chemicals to do that. In electrical terms, the higher the frequency, the lower the impedance of CT. As CT is in parallel with RT, the overall resistance of the battery drops the higher the transient frequency. Eventually, CT short circuits RT, leaving only RS. Battery models can be refined nearly endlessly depending on what behavior needs to be modeled as accurate as possible. This one includes self-discharge and a transient response for different frequencies, but for this tester the middle model will be good enough. After discussing so long what's inside a battery, let's see what's inside the BM550. After removing the 4 self-tapper screws on the back, it comes apart easily. A surprisingly small PCB with a connector for the probes, a couple of chips, an enormous resistor and an LCD screen. In this picture it's clear how small that PCB is compared to the housing, which isn't massive to begin with. Most noticeable is that gigantic 11 ohm resistor with an unmarked, probably MOSFET transistor as a switch below. That is what causes the pulses. 12 volt divided by 11 ohm is about 1 amp, which is what the scope showed. This also means that at 24 volts the pulses will be 2 amps and half an amp at 6 volts. Speaking of different voltages, there's a 7333-1, a load drop regulator that provides 3.3 volts for the electronics. It can deal with up to 30 volts according to datasheet. The BM550 is rated for up to 32 volts, and I guess they rely on some diodes to drop the voltage somewhat. The tester is protected against wrong polarity. The diodes should be these up here, although both are Schottky. The top one is rated 4 amps and probably used for the pulses, while the lower one can handle just 1 amp. Everything is run from the microcontroller SWM181 from Sinwit. I only found a Chinese datasheet, but it seems to be based on an ARM Cortex and has the usual things in terms of general purpose I/O, including ADC and an LCD controller. A second chip has been carefully lasered to remove its markings. On the left we see 2 connectors, one for the LCD backlight and the other one for the 2 probes. The probes are using 4 not very thick cables, which explains why they are so flexible. Are these truly Kelvin probes? Okay, I see one cable going to the front of the clamp, and the black lead is kind of tucked below the handle and connected to the clamp body. The cable to the front goes through this metal insert, the teeth if you want, which sits on a white plastic insulator. And the rivet that holds the teeth and insulator is itself going through an insulated insert. This really looks like a proper Kelvin arrangement, with the metalwork of the whole clamp being one connection and the toothed insert the other. I tested continuity for both probes. This here is the red one. Since I needed access to the teeth, I jammed a piece of wood into it, open wide as a dentist would say. The red wire on the connector is attached to the outside, while the yellow wire is not. The red wire is not connected to the teeth, but the yellow wire is. Using proper Kelvin probes allows the BM550 to compensate for any drop over the probe wires, so they can get away with relatively thin and flexible cables. To be able to do that, both parts of the probe needs to be connected. It tests this, and if you connect only one part, like here, the display flashes until both parts of each clamp are properly connected. Impressive attention to detail. How does it do its measurements? If you recall, it shows CCA, state of health, state of charge, battery resistance and battery voltage. I hope it becomes clearer if I replace the battery with a battery model and a BM550 with a very simplified schematic. The meter does 2 things. It measures the voltage directly at the probes using the Kelvin clamps, and it produces a train of pulses by connecting the 11 ohm RL across the battery at about 125 Hz. As a start, because of the transients caused by this measurement, RT is nearly bypassed by the low impedance of the capacitor CT. When the transients are not produced, the meter measures VB. With the load of the transients, it measures a lower voltage called VL, with a known load resistor of 11 ohms and using this formula, which is easy to derive, the value of Rs. So we know how it gets Vb and Rb, which is simply Rs. I believe the microprocessor simply uses a lookup table or some custom scaling to derive CCA and state of health out of these two values. State of charge, or SOC, is probably derived from Vb. I did a couple of tests and SOC is really very simple. It all depends on the selected nominal battery voltage at the beginning, which is really the only reason why you have to select it. Nothing else depends on it. Let's look at the blue traces first, which is the state of charge readout in percent over Vb on the x-axis. On the upper left is the 6-volt case. A Vb of 6.1 and below is simply 0%, and anything above 6.7 volts is 98%. It never shows 100%. The range between 6.1 volts and 6.7 volts is equally divided to produce 0 to 98% readouts. Exactly the same for 12 volts on the upper right. Anything between 12.2 volts to 12.8 volts will produce a near linear 0 to 98% SOC. Anything outside, either 0 or 98%. And the same for 24 volts, where the range for 0 to 98% is 24.1 to 24.8 volts. I looked at several online charts of lead-acid open circuit battery voltage versus SOC, and they are all different and also depend on the type of battery. All I can say is the values used by this tester are certainly in the same ballpark as these online charts. Whether they apply for your battery is something you need to decide. Also, the SOC produced by this tester is of course nonsense for batteries that are not lead-acid 6 volts, 12 volts or 24 volts. Now to the red traces. These are the measurement errors of Vb compared to the BM869S connected directly to the same point. In all three tests, the BM550 is reading too low. About 1.7% for the 6-volt range, improving to about 1% for 12 volts and 0.75% for 24 volts. That accuracy could certainly be better, in particular since the readout is with 2 decimal places like 12.3 volts, making it look very accurate but really isn't. I recommend to ignore the last digit of the Vb readout. Okay, how about Rs then? My first attempt looked like this. I used the power supply to simulate a battery and inserted a known Rs into the connection to the BM550. Before each test, I measured Rs with my 3441A using the same connection as the BM550 with as little disturbance as possible. This is particularly important for very low resistance values because just small movements changes the contact resistance. The results are confusing. For any Rs above 0.2 ohm, the BM550 reads increasingly to low values, exceeding 10% error at 0.5 ohm, a 50% error at 1 ohm, and so on. I can understand this part here because when using resistances of 0.1 ohm and lower, it's really difficult to avoid errors in my setup. But the rest? A bit of speculation from my side. If you recall the diagram shown earlier, the simplified schematic of the BM550 was actually missing an important bit. The meter is powered from the battery under test. I measured that in the idle state, the meter draws about 33 milliamps at 12 volts. This means Vb is no longer the true Vb because of the voltage drop on Rs and Rt caused by the current needed to feed the meter. In a sense, the BM550 is a very bad voltmeter with an input resistance of not meg ohms but only about 360 ohms. For the case of measuring a higher Rs, however, this means this equation is no longer valid because Vb is increasingly wrong. Since good batteries have Rs in the tenth of milliohms, that is probably not too much of an issue, and for worn batteries with high Rs where this effect becomes noticeable, the battery is pretty much a case for recycling anyway. Of course, this limits the value of the BM550 to batteries that, when good, can deliver a reasonably high current and hence have a low resistance. Button cells and similar tiny batteries cannot be tested with a BM550. Just for the record, I did consider whether the error was caused by using a power supply instead of a real battery, so I replaced one test with a real battery and a 1 ohm RS, and the result did not change. Speaking of button cells, I was curious how low the voltage of the BM550 can be because I want to use it on 18650 cells. You can't select less than 6 volts, but we know that this setting is only used for the SoC readout. The meter itself works fine with 3.3 volts. It works even at 3 volts, but the display is very dim to read and the reported VB is never lower than 3.35. So the minimum usable battery voltage is 3.35 volts. Still, that makes the BM550 very suitable for testing single 18650 cells, which is great. The only issue is that connecting the big Kelvin clamps to this battery holder is a bit tricky, and I'm truly thankful that the BM550 shows whether they are properly connected or not. Running the test using the default of 500 CCA, which doesn't really matter here since I only want the resistance. For this old 18650 from a broken vacuum cleaner, the resistance turns out to be 61 milliohms. Let's keep that value in mind for later. My first test setup to verify this uses two multimeters simultaneously. The first measures VB and the second the current. I use a load resistor of 100 ohm. The reason for the high load resistor is that I don't want the battery to start noticeably discharging during the test. The yellow fluke is measuring current and the red Bryman the voltage. VB is currently 4.173 volts and some change. Since I'm interested in the voltage drop, I can save myself a calculation by switching the Bryman into relative mode so it shows the drop directly. To minimize the effect caused by discharging the battery, I press hold simultaneously on both meters as soon as the readouts are stable and disconnect the battery. Finally, a good use of the hold button, eh? This gives me time to take in the readouts and do the calculation without changes due to the 18650 cell discharging. The voltage drop was 7.1 millivolts and the current 40.145 milliamps. Plugging these values into the calculator, the resistance can be easily determined to be 177 milliohms. According to the battery model, the BM550 has measured RS of 61 milliohms, while I just measured RS plus RT, which is of course larger. But what I want is to verify if the BM550 is showing the correct value for low RS, especially since we already know it has a problem with large RS values. The only way to verify this is to switch to AC measurements at a sufficient frequency so that RT gets eliminated. This is how that looks. I use a generator to produce a 1 kHz sine wave AC voltage. A 1 microfarad capacitor blocks the DC of the battery of flowing back into the generator, which would probably destroy it, and I added a belt and braces 50 ohm series resistor to not short circuit the generator in any case. That extra resistor should not be necessary because at that frequency the 1 microfarad capacitor has an impedance of 160 ohms. Otherwise the setup started out exactly the same way as before, except I switched both multimeters to AC mode, but now we are no longer looking for a DC voltage drop, just a pure AC voltage across the battery. That setup turned out to be a failure. I don't know how safe it is to run large AC currents through an 18650, so I kept it very moderate. As a consequence, the AC voltage across the battery should be very small, about 1 millivolt, which is hard to measure. The Bryman showing the AC voltage kept incrementing because it picks up the noise. It continued doing that even when the current was off. Just connecting it to the 18650 and nothing else shows noise of more than 4 millivolts AC already. Shortening the leads and it goes back to zero as expected. I tried different meters and shielding, but in the end I used my freshly repaired and calibrated Datron 1030A for the voltage part and increased the current a little. The fluke is not immune to noise either, as you can see in the readout is not zero, but the real current is sufficiently higher to make this not matter. When the AC is connected, the current is 16.645 milliamps. The Datron is also showing some noise voltage, which we have to subtract from the reading. It's a bit fluctuating, but let's take the noise at about 0.193 millivolts. When the AC is connected, it jumps to a value of about 1.265 millivolts. And when disconnected, the value goes back to roughly the previous reading. With these values, the AC voltage over the battery produced by the generator is 1.072 millivolts, and with the measured current, this results in 64 milliohms, which is remarkably close to the 61 milliohms measured by the BM550. You may have noticed that I used 1 kHz while the battery tester is only using 125 Hz. The reason is that with a higher frequency, my 1 microfarad capacitor represents 160 ohm, which drives a sufficient amount of current to make the measuring easy. I could not find a non-polarized cap with a higher value in my stock, but for the record I did try the same test with 100 Hz, at which frequency my 1 microfarad capacitor represents 1600 ohms, and doing the measurement is a lot harder with the smaller currents and voltage, but still resulted in a very similar result. Now that we have RS from the AC measurement and RS plus RT from the DC measurement, we can determine what RT is, namely 113 milliohms. Sadly, I can't measure CT, but it must be a very high capacitance to be practically 0 ohms at 100 Hz. Of course, the neat confirmation of RS measured by the tester could be a coincidence, so I tried the same with a different battery. This is a pack with 6 beefy nickel-cadmium metal hydride cells in series. The tester produced a value of 54.54 milliohm, and my test came back with 55.37, which is encouraging. This is a few years old 12-volt lead-acid battery for my UPS. I had replaced it recently because the UPS time was down to only a few minutes instead of the nearly 1 hour it normally achieves. It was meant for recycling, but for this video I hooked it overnight to this charger, which also had a recondition mode, and selected that. It's a 7 amp hour battery, and according to the chart it has a CCA of 130, so I selected that and ran the test. I'm happy that it still shows poor, because I very much doubt this battery has much life in it left, reconditioned or not. The resistance is 65.6 milliohms. I ran my AC test and it came back with 52 milliohms. Given that the AC voltage was just 0.655 millivolts and my struggles to measure it with reasonable accuracy against noise, I think that still confirms the BM550. Also, I later ran a discharge test of this battery, and instead of 7 amp hours it only had 1.6 amp hours left. This confirms the BM550 rating it poor. Finally, a real test using somewhat shaky mobile phone video. This is the original 68 amp hours battery of a 9-year-old Volkswagen Golf. According to the table, this should equate to slightly above 520 CCA. I forgot to change the setting and just used it on 500. It should not make too much difference. It is rated at 405 CCA, still good, happy to see this. The resistance is 6.4 milliohms. And exactly the same type of battery here in a 7-year-old Seat. This time I remembered setting the CCA. The tester rates it as good at 488 CCA. Resistance is just 5.3 milliohms. The car was not used for 2 weeks and had only relative short trips before in very cold weather, which explains the low charge. To conclude, I'm quite impressed by the Kingbolen BM550. It certainly works for car and motorcycle batteries, and if you know how to interpret the readouts, it's a good and convenient tool for testing all other kinds of batteries too. I'm using it now extensively for checking the resistance values of recycled 18650s, of which I have a lot. If you like my videos, don't forget to subscribe. And it would be great if you decided becoming a Patreon. That would really help this channel. The link's in the description. As a Patreon, you always get early access to videos, a blog and other exclusive content. Thanks for watching.